So in example 1, we saw that if we are taking group elements to higher and higher orders, we eventually cycled through and came up with the identity. We got the identity eventually in all the cases that we looked at. And this gives rise to a definition, actually to two definitions. Let's read it together. Let G be a group and let little g be an element in G. Then there are two things associated with a group that we call the order, where we use the word order. So it happens twice right here. The first idea is the order of a group. So the order of a group is written as absolute value of G right here. And that is just the number of elements in G. So that is something that hopefully is familiar. So the order of a group is really the number of elements in the set of our group. But then we have the second idea, and that is the order of an element. That is written using the similar notation of the absolute value, but now this G right here is just a group element, and that is the smallest positive integer n that we can raise G to get the identity. And so if we have a multiplicative group, then we have G, the notation is this exponentiation notation, but it really means you take G times G times G times G n times. If we are talking about a multiplicative group, it's addition, repeated addition. So you take G and you add it to itself n times. So G plus G plus G plus G n times. And so if you get the identity back, then the smallest number of times that you are using that operation of G on itself, that is called the order of that element. If such an integer does not exist, then we say that G has infinite order. Let's look at some examples. Let's look at some examples to just clarify what we're talking about here. So when we're looking at our group U7 from the previous example, so in U7, what does this look like? Well, what is the order of U7 itself? That is the number of elements, and if you go back up, let's see. So here is U7, and it has 1, 2, 3, 4, 5, 6 things in it. So that means that the order of U7 is 6. And similarly, that subgroup H1 that we encountered, that had 3 things in it. And the subgroup H2, that had 2 things in it. So these are the orders of groups. So the number of elements in that group. But then within U7, we looked at the order of several elements. We looked at 2, we looked at 3, we looked at 4, and actually we also looked at 6. And so what is that? According to our definition, it should be the smallest positive integer such that 2 to the n is equal to the identity. So we want an n so that 2 to the n is equal to our identity element right here. And if we are going back up, the smallest such integer was 3. We needed to take 2 to the third power, 2 times 2 times 2, to get the identity back. And so the order of 2 is 3. And similarly, the order of 3, I'm doing a lot of scrolling here, but the order of 3, how long did it take to get 1 back? Well, we had to take 3 to the 6th power to get the identity. So this was 6. And then similarly, the order of 4 in this group is 3, and the order of 6 is 2. You can convince yourself that that's the case. And so that is the order of an element. And you'll be doing a lot of exercises with this. We will be using this a lot, so hopefully it will become familiar to you. So over here we are talking about the orders of elements. So that's the important thing. The order of the group is very different from the order of an element of the group. The second idea that I want to talk about is the definition of a subset of H of G. And that is not that complicated, really. So a subset H of a group G is itself a group under the operation of G. So the same operation that we also had in G. So if that's the case, if we have a subset and it is itself a group under the operation of G, then we say that H is a subgroup of G. So a subgroup is a subset that in its own right is a group using the same operation as in the bigger group G. And there are two pieces of notation that I want to introduce that we use. So one is H less or equal to G. And that means that H is a subgroup, possibly G itself. So G is its own subgroup. So possibly H is equal to G, so it's inclusive. That's why the less or equal is there. And if we want a proper subgroup, we are using H just with a less than sign for G. So that here H can't be equal to G itself. It's definitely a smaller subgroup of G. But we are using the less or equal sign to denote that H is not just a subset, but it's actually a subgroup.